So here we start talking about organic compounds. And the distinctive feature of all organic compounds is that they contain at least carbon and hydrogen. Like if they do, it's an organic compound. They may contain other elements, but carbon and hydrogen are the absolute must. So for example, if you consider carbon dioxide, it is an organic compound, while methane is organic compound. Again, they may contain metals, they may contain nonmetals. The most common nonmetals that you're going to find, especially in biological materials, oxygen, sulfur, nitrogen, and phosphorus, those are found in various biological molecules. And halogens are commonly found in just, organic compounds. It can be, and it can be metals. Okay? They are everywhere. Most of the materials in this room are organic, actually. Okay? And when you write the formula, you always write carbon first, hydrogen next, and then, it depends. So, organic compounds, bonding, covalent, melting and boiling points are low. For instance, your oil or gasoline. Okay. Many of them are flammable, however, to a degree. Okay. And I do not like that statement, to be honest. Not soluble in water. Really? What about glucose? Or sugar? There are organic compounds that are not soluble in water. But that statement is overgeneralization. So if you compare organic and inorganic compounds, if they have similar molecular mass or formula unit mass, they may have vastly different physical properties. For example, this is the molecule of propane. Okay? You can calculate the molar mass of propane. It's a gas, but it's going to be 44. Okay? And then you have sodium chloride. Together it's 58. So not that different, but sodium chloride has very, it's ionic compound, it's soluble in water, and don't burn in air and have high melting and boiling points. Okay? So if we will try to find sort of an average, a distribution of melting and boiling points, overall inorganic compounds have higher melting points. Okay? So this is the comparison between sodium chloride and propane. Okay? So ionic sodium chloride have really high melting and boiling point, while propane is very low. And covalent ionic compounds do not burn, while organic compounds do. Now, I deliberately ignore the solubility statement, because I can give you an ionic compound, barium sulfate, which is as ionic as can be and is not soluble in water. And I can give you an example of organic compound, sucrose, which is totally covalent and perfectly soluble in water. But the point is covalent and ionic. And the first group that we start with when we talk about these compounds are hydrocarbons. Now, the name implies that the only elements that comprise those compounds are carbon and hydrogen. The universal feature of all organic compounds is that carbon has 4 bonds and these bonds are oriented in space in the form of tetrahedron. So what is a tetrahedron? So imagine you have a triangle, and you make this triangle the base of a pyramid. Okay? The apex of the pyramid is here. Does that make sense? So that line, I actually want to change it. Like that dashed line is in the back. Okay, so this is a tetrahedron. Hydrogens are in the apexes and the carbon is in the center. This bond configuration is universal for all saturated hydrocarbons. Saturated hydrocarbons are the ones that do not have any double bonds, only single. The simplest organic compound is methane. It has a formula of CH4, and in this compound the carbon central, that is shown as the black sphere on the left, forms 4 bonds with hydrogens located in the corners of the tetrahedron. Okay? Now, that tetrahedral conformation, shape, is dictated by the electrostatic repulsion between the electrons forming these 4 bonds. However, when we discuss organic compounds, we sometimes use the molecular formula. Okay? For methane, the molecular and the condensed structural formula are the same. We can use expanded structural formula to show all the bonds in the 2D projection, 2-dimensional projection. We can use wedge dash model. Now, I want to talk about this, and I really want your attention at the screen of the white screen here. Okay, we project it. So, otherwise you will have troubles understanding wedge dash model. The bonds that are represented by a regular line are the bonds positioned in the plane of this screen. Does that make sense? Like this. This bond is in the plane of the screen. It doesn't go behind it or in front of it. Make sense? The wedge tells you that the hydrogen at the end of the wedge is supposed to stick out in front of the screen. We can't do that, but that's 3D representation. Does that make sense? The dashed bond shows you that the hydrogen at the end of it is behind the screen. And again, the lines are within the screen. Now, look at the ball and stick model. It becomes sort of obvious, right? Right? That they're not two-dimensional. Okay, and this is the space filling model. But let me ask you this. When you look at the photograph, at any photograph, can you tell the three-dimensional object? Basically, like, can you understand the shape of an object? Three-dimensional shape, yeah? But the photograph is two-dimensional. It's a plane, right? It's flat. Because of the cues. Clear? Or if somebody draws, like if I would draw a cube like this, you would understand. You would understand my clues, right? So this is wedge shaped. Okay. So another alkane, saturated hydrocarbon with two carbons, it's called ethane. Okay. So the bond orientation is still tetrahedral. The only difference that for each carbon, one of the positions in that tetrahedral orientation is taken not by hydrogen, but a carbon. Okay? So if you look at this ball and stick model, you can kind of appreciate that. Okay? So now you start seeing the difference between the collapsed or condensed structural formula and the molecular formula. Can you tell me the molecular formula of ethane? Answer is literally on the screen. C2H6. Yes. Okay? So we often, in most cases, we do not. I personally prefer to use the condensed structural formula. Okay, sounds good? So predict the shape around each carbon atom. Are there any double bonds? Okay. When there are no double bonds, is it considered to be saturated? Please start recognizing leading questions. Is it considered to be saturated? Yes. That was a leading question. If the hydrocarbon is saturated, all carbons are tetrahedral. Unsaturated, it becomes a little bit more complicated. So the chemicals, the methane and the ethane that we talked about so far, belong to the large class of organic molecules called alkanes. So alkanes always contain carbons and hydrogens. They can be linear or branched. And they only have single bonds. They are saturated hydrocarbons. This is what describes alkanes. All good? So the names of the alkanes formed according to nomenclature developed by IUPAC. So a bunch of nerds that are also pedantic bureaucrats. Okay? Names of all alkanes end with A and E. And they can use prefixes, they use prefixes to tell you the number of carbon atoms in the molecule. So these are the names of the first 10. Okay? Now what I'm going to do, I'm going to highlight the ending so you can see the first part. Meth, eth, prop, but, pent, like pentagram, so 5, hex, 6, like hexagonal, hept, 7, oct, like octave, 8, non, that's 9, and dec, like deciliter or decathlon, 10. You only need to know first 10. Does that make sense? So, can you encounter the question, what is the proper name for a compound C4H10? Yes. Can you encounter the question, what is the proper IUPAC name of a compound C14H30? No. Now, few more things to discuss while we are at it. First, wait, I have a brain fart. I wanted to talk about, first, the easy part. There is a universal formula for alkanes. It is C, so it basically shows you the universal relationships between the number of carbons and number of hydrogens. So this is C. If you have N carbons, you can choose N. Like, let's say N 100. You're going to have 2N plus 2 hydrogens. So if N is 100, the number of hydrogens will be 202. Okay? Second thing that I wanted to discuss is the line angle formula. Why? Because this table contains an absolutely glorious error. Let me demonstrate this error to you. So what is a line angle formula? Let's say we have a molecule. Now, watch me. Don't pay attention to the table yet, okay? You have a molecule of ethane. How many carbons there are? 2. These dots are carbons. These carbons, are they connected? Yes, by a bond. How many bonds can each carbon form? 4. So in this depiction so far, how many bonds from each carbon did I draw? 1. So each carbon has how many bonds left? 3. These bonds will be formed with what element? Hydrogen. So you can extrapolate. You don't need hydrogen. See what I'm saying? So this, we do not draw dots. All we draw is a line. Now, let's say we have propane. We position carbons in a zigzag. We do not draw dots, so we do this. The rule is the end of a line and an angle are carbons. Am I making sense? So just to test that we are on the same page. How many carbons are in this molecule? 6. 4 angles, 2 ends. Does that make sense? Trick question. How many carbons are in this molecule? Say again? No, not 0. No. 1, 2, yes, 2, 3, 4, and there is an angle 5. Crossing is a carbon. Okay? Make sense? Huh? Oh, okay, I thought. How many carbons are in this molecule? No, 4. That's that. Okay? So now I'll go back to this table. There's a mismatch. So it has to be shifted. Does that make sense? Okay. I love finding those mistakes. I know it's very condescending, but I feel myself superior. Okay. Condensed structural formula. When you look at this, guys, doesn't tell you how bonds with hydrogens are organized, but you can figure it out yourself. So basically it tells you that this carbon, for instance, second from the left, this carbon, it has 2 bonds with other carbons and 2 bonds with a hydrogen. Make sense? So this kind of, I don't know why we need to do that, but it's pretty obvious that in expanded formula we expand all hydrogen bonds with hydrogen, but then we condense them, and this is what we have. Okay, and same as for carbons that are in the middle of a chain. You've already seen all those representations. Molecular, space filling, ball and stick, structural, and line angle. Expanded structural formulas are required when you need to represent, like, the loss of hydrogens, for instance, right? The wedge-shaped models are usually required if the shape of the molecule, the conformation of the molecule, plays an important role. Okay? So, structural formulas for butane. This is an expanded one. Okay? Now, why would you have all those 6 different formulas? Depends on the reaction that you're trying to illustrate. Sometimes you want carbons aligned from top to bottom on the page, sometimes from left to right. For the most part, it is left to right, one line. Does that make sense? These line angle formulas are also equivalent. And as you can see, they have 2 ends, 2 angles, so 4 carbons. Alkanes can form a cycle. And sort of obvious that the smallest number of carbons that can form a cycle is 3. Right? You cannot form the cycle out of 2, it's just line. Right? Am I making sense? So, the universal formula, what would it be then? Try to figure it out. So this is CnH to N plus 2. What will be the universal formula for cyclopropane? What is 6 in relation to 3? 3. What do you need to do with a 3 to get 6? Multiplication, not addition. Multiply by 2. There we go. Okay? All cycloalkanes are like that. If you want medical relevance, cyclopropane was used as the anesthetic. You know, like dinitrogen oxide, N2O, the laughing gas, is used now. This was used as anesthetic. The use of it was stopped. It was not because of the toxicity. It's extremely flammable. Like, extremely flammable. Okay? So cycloalkanes, you will have a chance to play with molecular models next Monday. Okay? And I can tell you, the most stable cycles are the inorganic chemistry, the cycles that contain either 5 or 6. 6 is the magic number. Cycle formed out of 6 elements is the most stable cycle. Okay? Does that make sense? So cyclohexane is nice liquid, and it's very stable. Cyclopropane is extremely combustible. Now, within the alkanes, you can find what's called substituents. Okay? When hydrogens are replaced by something else, and that something else is attached to a chain of carbons. Okay, so this brings us to the conversation of isomers first. Structural isomers have the same molecular formula, but the arrangement of atoms is different. So, for example, here is an example of 2 molecules of, I want you to name it. Do you remember the 4 carbons? The B word? Butane, yes. This is butane. Okay? So, what is the formula of butane? C4H. Nope. How many hydrogens? 10. Do both molecules have the same formula? Molecular formula. Do both molecules have 4 carbons? Do both molecules have 10 hydrogens? Yes. Both molecules have 10 hydrogens. Yeah? So, but the arrangement is different. Okay? Make sense? So this is butane. This is isobutane. Okay? And they are different in terms of properties. Okay? So, let me ask you this. What is the name of a compound with 3 carbons? Propane. Yes, like propane tank, right? So, What is the name of a compound with one carbon? The simplest one. Methane. So technically, you can say that there's a propane, right? 3 carbons. And 1 hydrogen is replaced with a CH3 group. Okay? All good so far? Yeah? So now we're going to try to organize. Do you mind if I'm going to do the line angle formula for brevity? All good? So this is your pentane. So we're going to focus on carbons. Is this correct? Check me. Yes. Now, how many carbons? 1, 2, 3, 4, 5. Right? All good? How many carbons? There you go. So, either this or this or this. Now, at this point, are you comfortable with line angle formulas? Yes? Okay, because it's going to save us time in the conversations. So, types of the substitutions. Alkyl group. Let's talk about it. The groups of carbons. Let's play with a couple of them just to exemplify what I want to say here. Listen. I want the name. Methane, right? This is the ending. Now, if I want to use that CH4 and attach it to another hydrocarbon, I have to ditch a hydrogen. Does that make sense? To free up, like, this is your methane, right? But I want to ditch one hydrogen in order to open up a bond. So it can form a bond with another carbon, right? So first of all, the formula will be CH3. And instead of ane, it's going to be methyl. Okay? One more thing. This is ethane. If I want to stick it somewhere, I need to ditch a hydrogen. Do you agree with me? Yeah? So it will be something like this. Okay? I opened up the bond, right? And the name will be ethyl. What is the universal formula for alkanes? CN H 2N plus 2. Okay? What will be the universal formula for alkyl substitutions? If you need to ditch one hydrogen, 2N plus 2 will turn into 2N plus 1. That's it. Okay? That makes sense? So if my substitution is C6. It's going to be H13, and that's going to be not alkyl, but hexyl. Okay. Halogens can serve as substituents, and based on what halogen we're talking about, these are we can call it a prefix we can use. So this is a summary, okay? We're not going to go into the weeds of isopropyl or isobutyl. At this point, we don't really need this. We're going to jump straight to naming. And I honestly consider this not fair to you, because we didn't talk about the rules. So how would you name that compound? So how many carbons? Again? How many carbons? Which one, this? No, that's not a carbon. That's Cl. So how many carbons? Wait, how many?
Five.
Dude, like seriously, it's not even math. It's counting.
So is it 5?
1, 2, 3, 4, 5, 6. That's carbon, CH3 group. Okay? What is that? Chlorine. Okay. So one way to name it is chlorohexane. There's only one problem. When we name hydrocarbons, the core name here must form a single line, a single chain. The 6 carbon, do they form a single chain? No. What is the longest chain? How many carbons are in the longest chain in this molecule? 5. Everybody agrees with me. So 5 pentane. Okay? Does that make sense? This group, which is methyl group, at which carbon it substitutes hydrogen? The number. You can't be serious. The numbers are literally on the screen. Number 3, yes. That's number 3, right? So, three methyl. What about chloride? At which carbon does it substitute? 2. 2 chloro. Okay? Now, I can't really ask you, is this name correct? Because you can't really judge, but it is. But I'm going to give you a challenge. Can I number them from right to left? Say again? I just did. No, I just did. I just numbered them. What the number on methyl group will be then? Like, so it's going to be 3 methyl, right? What is the number on chlorine group will be then? So here's my question. Which name is correct?
First one.
First one. Why?
Because we always go from left to right.
Nope. That's not the rule. There are three main rules for alkanes. Longest chain. Minimize I'll explain the positions of substituents. It's very simple, seriously. In the red name, in the first name, what is the sum of the numbers? 2 and 3? 5. In the blue name, what is the sum of the numbers? 3 plus 4? 7. The sum of all those numbers must be minimal. Does it have any chemical sense? No. A bunch of nerds agreed to do that. That's it. I'm not even kidding. This is what humans could say, let's make it maximal. It would work. We just agreed that it's got to be minimal. Making sense? Now, substituents must be in alphabetic order. In the first name, are they? Yes. In the second, no. Methyl cannot go before chloro. Does that make sense? So, when you have a single, even when you have single substituent on the alkene, you need cycloalkanes. So here's what you need to do. You have a single substituent, which is ethyl, right? When you name cycloalkanes, you always go off of the cycle. Am I clear? Yes? Now, if you have only one substituent, you do not assign it a number, because all carbons in the cycle are equivalent. Make sense? It doesn't matter where you start counting, so you don't need really. Okay? Now, what do I mean by what's the word? Going off of a cycle. How many carbons? 6. So it is cyclohexane. Correct? Add a substituent. How many carbons are in the substituent? Is 8 more than 6? Yes, but what are we going to do in this case? What is the longest chain? 8. So in this case, 8 is octane, okay? What is the name for that originally? Cyclohexane, but now it is a substituent, so cyclohexyl, do we need to add number? Yes, because it's not a cycle anymore. So it's 1 cyclohexyl octane. Okay, makes sense? Let me see. Okay, so we're gonna finish alkanes before properties and call it a day. Okay. So let's draw this. Okay. So heptane, 7 carbon, right? 2, 3, 4, 5, 6, 7. Make sense? When you draw, hear me out. You're right. When you draw, we usually do it from left to right. When we name, that doesn't matter. So 1, 2, 1 chloro. So let's say this is going to be 1. Okay? All good? Dimethyl means that there are 2 methyl substituents. So this is 1 because it's at the first position. And this is another one because it's in the second position. I'm going to ask you a trick question. Can I draw this? I just did. Would it be wrong? No. It would be ugly because here's the deal. What I like about line angle formula, it gives you a little bit better appreciation of what the molecule is shaped like. So in the real actual molecule, 2 methanes almost like next to each other, they're going to repel. They're naturally going to be on the opposite sides, so to say. Okay? So 3 bromo, 1 chlorobutane. Butane, how many carbons? 4. That's your Cl. How many chlorines? That's a stupid question. 1. How many bromines? Well, no. That's a position, remember. Okay, I need to update this. So, just 1. Hear me out. The numbers are equivalent to the position. Di, 2 substituents. Tri, 3. Tetra, 4. And so on and so forth. Okay? Does that make sense? All good? So, we draw 4 carbons. Okay? Doesn't matter where we number them. So 1 chloro, 3 bromo. All good? Now we need to figure out the number of hydrogens. The very first carbon, how many bonds does it have left? They form 4. 2. Next, how many bonds? This one, how many bonds? The third. Just 1. And the last one? This is your line angle formula. All good? Okay. Now I'm going to give you sort of a kind of trick question. So what I'm going to do, I'm going to do this. Yeah, that's fine. Okay, so I replaced all hydrogens in butane with fluorines. Okay, right? I can do that. It is possible chemically. How many fluorines total in my molecule? 10. So I can call it decafluorobutane. Deca means 10. Right? Good? Make sense? Yeah? Did I replace all hydrogens? Are there any hydrogens left in that molecule? What people use often, it's not an IUPAC nomenclature. Per means that all hydrogens are replaced with the same kind of atoms. You may wonder why I specifically looked at all hydrogens replaced by fluorine. Are you familiar with forever chemicals? Ever heard about them? So, chemicals like perfluorobutane, that mostly it's like perfluorooctane and stuff, they are used, for example, for non-stick, like, do you have any non-stick skillets at home? The non-stick surface is made out of perfluoroalkanes. And they are so inert that nothing, not a living thing, can do anything to them. When they leak into the environment, they're going to stay there forever, and they become more and bigger problem. All of us, we carry that stuff. It's in food, it's everywhere. Okay? And it's a pretty significant problem because it disrupts certain metabolic pathways in various animals. Okay? Now, the idea of, thermonuclear war and elimination of humanity doesn't seem so horrible, does it? Right. All right, folks. So we're gonna talk about the properties of alkanes on Monday after the class. Like we're gonna do the lab, and then we're gonna finish this. See you then. Okay. So we basically covered the structures of alkanes last Wednesday, but I'm gonna now we're gonna talk about some properties of these gases. So alkanes that have 1, 2, 3, or 4 carbons are gases, and we use them as heating fuels. Okay. So obviously it's a type in lectures 5, 6, 7, and 8, they are not gases, but can also be used as fuels. Okay, so 5 to 8, and they are liquids at the room temperature. Okay, so 9 alkanes with 9 and to 17 are heavier liquids, and they are usually found in things like motor oils, mineral oils, kerosene, diesel, and fuel for the planes. 18 or more paraffins are solid and waxy at the room temperature. And petroleum jelly is the mixture of different hydrocarbons. Okay. Now, before we get to the usage of alkanes, I want to highlight something. So pentane, hexane, heptane, and octane, right? Those are liquid alkanes. They fairly light, and they comprise a huge chunk of the gasoline that you pour into the tank of your car unless you drive an electric. Does that make sense? Now, did you ever ask yourself, what is the number? Like you put, 87, right? Gas. Or 89, or if you drive Ferrari, 91. What does this number mean? Okay, huh? It's an octane number. If you want me to hear you, just yell, huh? What did you?
Sure, that's all.
It's an octane number. And so when you think about the way cars operate, right? The fuel is injected into the engine. Am I making sense? And then it burns very quickly inside the engine. Okay? Now, there's a very small step from burning quickly to detonating. Does that make sense? The greater the octane number, which I believe corresponds to sort of like percentage of how this relates to pure octane, okay? The greater the octane number, the less likely the gas is to detonate. Now, high-performing engines, like the ones you're going to find in Italian sports cars, right? The compression that they produce, compression of the gasoline is much greater, so the detonation is more likely. So this is why in like super expensive cars with the really powerful engines, you're supposed to put not 87, but 91. I don't remember which one is the top one, like 93, whatever. Does that make sense? Now, another interesting feature is that where do we get gasoline? Like, how do we get gasoline to put in our cars? Where do we get it from? Huh?
Gas station.
See it?
Gas stations.
Well, yeah, but it doesn't just grow in the tank of a gas station if you water it enough, right? How does it? Where does it get there from?
On the oil.
They drill it on the ground.
From oil. We don't drill for gas. We drill for oil. Now, hear me out. A little bit of a chemical technology. So we drill for oil. It's pretty dense, right? Then we transport it to the oil refinery plant. And what do they do with the oil at the refinery plant?
They separate diesel, crude oil.
They separate it into fractions, right? When oil is pumped out of the ground, the alkanes, that methane, ethane, propane, and butane, they evacuate as a gas because gas is always there. Then the most volatile fractions, they make up gasoline. Okay? What's left makes up diesel fuel and kerosene. They say, I love how chemists are unaware. Where's that? When they separate kerosene and jet fuel, it's the same. Kerosene is a jet fuel. And then what's left is bitum, which is used in the preparation of asphalt. Okay? The sticky, gooey product. Does that make sense? But it's not only the separation. There is another thing that happens. They process gasoline after they separate it to increase the octane number. Okay? Make sense? The same reason when you buy oil for your car or you change oil, there's a conventional, there's a blended, and there's a synthetic. Synthetic oils are specifically designed to provide the best lubrication for the engine, while conventional oils are produced from crude oil, and the composition may not be stable. They little worse. Okay. This is the summary. And let's jump to solubility and density. Since alkanes are nonpolar, they're not soluble in water. Alkanes are less dense than water, Not all of them. If we're talking about motor oil, it is not less dense than water, okay? But first dozen, definitely. Are they flammable? We already discussed the crude oil ID, okay? That makes sense? Now, during the oil spill, the problem is not only that it's a film on the surface of the ocean, prevents oxygen exchange, okay? And if it gets into birds' feathers, it's really hard to remove. It's like, removing the oil, okay? So this is why you have to wash it. Now, there was a study looking at some bacteria that can actually eat the oil. And it turns out there are bacteria that can. Combustion. So in alkanes, the carbon-carbon bonds store enormous amount of energy. And if you burn them, you release that energy. Okay? So the product of the combustion of all alkanes is carbon dioxide and water. Do you follow my train of thought? Yeah? Here's the question. Gasoline, what does it consist of? What are we talking about? Alkanes, hydrocarbons, right? When they burn, they only produce carbon dioxide and water. Where does the pollution come from the cars? Like, why do we need all those catalytic converters and this and that? And they have to pass the emission test. What's going on? In this reaction, methane burns in the atmosphere of what gas? What is that O2? Oxygen. Is air pure oxygen? No. It's number one. This is why a lot of nitrogen compounds, pretty toxic compounds, are formed when engine works. Another thing, during the short time that the gas burns within the engine, a lot of gasoline molecules that comprise gasoline, they are not burned completely. And this is why we have a catalytic converter that kind of processes them, making sure that we release the minimal amount of contaminants. Okay? Butane. You see this butane burners? So these are the best for camping if you're into it, because they produce enormous amount of heat in a very short period of time and from the very small mass of butane, okay? Produces a lot of energy. So one of the things that you will need to do when we get into the, or chem questions on the exam, not on this exam, no, is to write the balanced chemical equation. And you can do carbon, hydrogen, and oxygen, but for the most part, it is not required. So what you get is carbon dioxide and water, right? So how many carbons you have on the left? 3. So let's put 3 over here, okay? Good? Now, oxygens, that stuff becomes a little bit complicated because you have that oxygen that is single. So put it aside. Don't think about oxygen. Balance hydrogens first. You have 8 on the left and the 2 on the right. So you need to put 4. Does that make sense? So hydrogens are balanced, carbons are balanced. We have 10 oxygen atoms on the right side of the equation and 2 on the left. We're adding coefficient 5, we balance the equation. Reasonable? Yeah. So alkenes and alkynes. This is an alkyne, also known as acetylene. It is used in welding because when it burns in the atmosphere of oxygen, you see triple carbon-carbon bond. Super high energy. When it burns, it produces insane amount of heat and very, very high temperature flames. Okay? So, alkenes and alkynes are unsaturated hydrocarbons since they contain double and triple bonds. The term unsaturated reveals that these molecules can accept extra hydrogen atoms. They're not saturated by the hydrogen. Am I making sense? And you can actually bubble hydrogen gas through those molecules and saturate them. They will accept this hydrogen. So, alkenes. Alkenes contain double bonds. Am I making sense? It can be one. We're going to deal with one, but they can contain many double bonds. Okay? The simplest alkene is ethene, also known as ethylene. Okay? So you have two carbons connected by a double bond. You can make this model yourself. What you're going to see is that this model, this molecule has to be flat. This is why the angle between the bonds, all these angles, are going to be 120 degrees. Okay? Now, ethene, or ethylene, is a very peculiar molecule because it is a hormone that plants produce. And this hormone controls ripening. Does that make sense? Those of you who buy bananas know what happens to them if you leave them on the counter for 4 or 5 days. They start getting over-ripened. Make sense? Now, bananas, last time I checked, aren't commonly produced in the United States, so we import them. And it takes a while for those bananas to reach U.S. shores. Usually it's a ship, right? You can't collect those bananas when they ripen because they're going to turn into a mush. You might as well just make banana bread right in the hull of the ship. So instead they are collected green, they travel, and then they treat it with ethylene on site to ripen them up and to sell. Alkynes is a triple bond containing hydrocarbon. Specifically, triple bond part is linear. Does that make sense? There's no other arrangement that you can come up with. So the bond angles here and here are 180 degrees. Okay? That's the last thing that we're going to chat about for today, and we're going to call it a day. So now, very important part, it's a different type of isomers. It's called cis-trans isomers. They demonstrate the position of certain groups relatively to a double bond. So if you connect two objects, let's say, let me ask you this. If you take two wheels and put them on a single axle, will they be able to rotate independently one from another? Like if somebody is holding an axle. You know what I'm talking about? Can you rotate one but another one stays? Dude. You're fucking kidding me, man. Imagine like a gym. Barbell, right? You put weights on the barbell. Can you rotate one way and another one stays? Now, what you're doing is you hypothetically put another stick between those two plates. So you connect them not with one axle, but with two. If one rotates, another one will rotate as well. Does that make sense? So this is a rigid connection. Clear? Which means you can have in the molecule of dichloroethene, you can have chloride atoms being on one side of the double bond or on the opposite sides. And you can't, there is no rotation around the double bond. Am I making sense? Independent rotation around. So it means that these two molecules, although they have same chemical composition, the atoms in those molecules are arranged differently. Okay? Does it make sense? Now, we can only apply this to the situation when you have two identical, usually identical substituents. We're talking about hydrogens, only two hydrogens, one at one carbon at double bond, another at another carbon. Okay? So this would be cis, same side. This will be trans, other side. So the good example, playing this, doing this with your fingers. Okay, so this is cis when your thumbs are on the same side. And this is trans where your thumbs are on the opposite side. So for example, this is a molecule of butene. Okay, so look, you have two carbons connected by a double bond. Okay? You put hydrogens on the same side, methyl groups on the same side. Okay? Cis. That makes sense? And if you flip them, that's your trans isomer. So here's what I want you to understand. Hear me out. Imagine that this is not a butene, but it is propene. No cis, no trans. You gotta have another carbon or similar substituent. That makes sense? If one of them has like two hydrogens, you cannot assign cis or trans isomerization. I don't know why we're talking about pheromones, really. Oh, this. Yes, now I realize. Because one of the pheromones called bombicol, okay, the effectiveness of the pheromones will depend on whether it is a cis or trans isomer, right? To wrap up on a more cheery note, why? So pheromones are chemicals that insects use to attract opposite sex. And they can sense it miles away. Why are we humans so interested in pheromones that attract insects? Unless we want to attract them for. What? Say again? I don't think there's enough money in the world that would force me to mate with a butterfly. We don't. Yes, they use it for mating, but why humans are interested? If there's a butterfly and it senses the pheromone, what's going to happen to that butterfly? It's going to do what? Fly towards it, right? So can you attract insects using pheromones? Yeah. Are there insects that you don't want just to attract? You also want them dead. Mosquitoes, yeah, mosquitoes are more complicated, yeah. No, there are, say again? Pests. Okay? No, seriously, pests. Agricultural pests, one of the methods of control are traps, which release pheromone and they go in the trap and then something like they die, something happens to them. They get zapped or something. But it's pretty effective. Okay? Does that make sense? All right. Monday after the exam, we're going to finish this. So when we name this cis and trans isomers, the only thing that we need to keep in mind is that we need to put cis if the substituents are on the same side, or trans if they are on the opposite sides, and they are placed, the prefixes placed before the name of alkene. So now cis or trans, and let's provide the full names. So the first one, first of all, how many carbons? Let's count the carbons, folks. How many carbons do you see there? 4. So I have 1, 2, 3, and 4, which means it's bute, right? Now, what is the position? Now, there's one double bond, right? Which means it's butene. Okay? So far, am I making sense? Now we need to demonstrate at which position the double bond is located, and it's located at the position 2. Remember, always the minimal number. Okay? Actually, I don't think I use the space that smart, so let's say 2 butene. Now, how many substituents do we have? We have 2 chlorines, right? So it's going to be dichloro. And what positions these chlorine atoms occupy? 2 and 3, right? So 2, 3, dichloro-2-butene. Now, is it cis or trans isomer? Same substituents are on the same side or on the opposite sides. So chlorines are on the same, right? Which means it's a cis isomer. Reasonable? Now, for this guy, it's going to be, I'm not going to torture you with all of it, trans 2, 3, dibromo 2, butene. And for this, since there are no substituents, the only thing that you need to write is that it's trans 2 butene. Okay, because no substituents will only show the configuration of a double bond. Does that make sense, y'all? Lyndon, question?
Yeah, how did you get that for the third one?
For the third
Why
one.
Is there no 2, 3?
Say again?
Why is there no 2, 3?
Because there are no substituents. Let me comment on that, okay? So let's take a look at these names, the first couple of molecules, all right? So this shows you how long is the chain. Okay? This shows you that there is a double bond. This shows you position of the double bond. Okay? This shows you substituents. That's the position of substituents, and this is orientation of substituents. So when you start looking at this molecule, this one, there are no substituents. Does that make sense? So we simply don't need this. So we have butene, which is a 4-carbon hydrocarbon with one double bond. We show the position of the double bond within the chain, and we show the orientation, that methyl groups are on opposite sides. Better?
Yep.
So why do we care about cis and trans isomerization? Because of the hydrogenation of oils. One of my favorite questions, and don't jump to the conclusions, just think for a second. What is cheaper to produce? Oil, like canola oil, or butter? What do you think?
Butter.
Dude, imagine how long you have to grow a cow so it starts giving milk, and then not all of the milk gets to become butter, right? So butter, anything that is animal. If you go to a grocery store, what's cheaper? A pound of chicken or a pound of, I don't know, beans? Pound of chicken, a pound of beans, of course, because the plants are cheaper to grow. Now, the idea was that we can produce a load of oil. It is liquid because it contains double bonds. What if we hydrogenate those double bonds, like here, okay, and we convert it into a single bond, and that will turn liquid oil into solid? I cannot believe it is not a butter, right? We call this shortening or margarine. Does that make sense? The only problem, and we're going to talk about it when we get to lipids, but I'm going to briefly mention this. The only problem is that the side product of oil hydrogenation trans-oleic acid. So this is cis-oleic acid, right? It's going to be trans-oleic acid. Turns out all trans fats are really bad for at least your cardiovascular system, and there is a significant evidence that they may contribute to increased risk of developing cancer. Okay? Now, I always found it amusing that the term benzene, which is in English assigned to that molecule, in Russian has like exactly the same word. It sounds exactly the same as benzene. In Russian it means gasoline. Okay? So it was isolated by Michael Faraday, and it is called an aromatic compound because it stinks. Okay? So obviously it wasn't called aromatic compound directly by Michael Faraday, but the idea was that this benzene part, this ring with 3 double bonds, was later found in many really aromatic oils and other compounds. So if you look at the structure, okay, let's start with this. So this shows you ball and stick structure. 6 carbons, okay, 3 single, 3 double bonds, and each carbon also connected to a hydrogen atom. Now, what's interesting about this structure is that you can draw two completely equivalent expanded structural formulas, these ones, with a different position of double bonds. So it looks like double bonds start jumping, don't they? Right? Yeah? So it was actually discovered later that the electrons that participate in the formation of those double bonds are equally shared between all carbon atoms. Does that make sense? So one of the representations that I don't think I will be able to reproduce, to draw properly, but imagine that we look at this molecule from the side, like we lay it flat and look from the side like you look at the plate, like this. Okay, like the edge of my palm, right? So it will look pretty much like this. This is the molecule. This is the carbons. And these are electron clouds. You can think of it as a donut of electrons on top and on the bottom, okay, being shared. So this is why the collapsed condensed structural formula often uses a circle inside. That circle demonstrates that instead of having three distinct double bonds, all electrons are in every carbon possession. Make sense? So a lot of aromatic compounds are very useful in chemistry, you know? So this is trinitrotoluene. So this would be toluene. This will be a compound called phenol. Does that make sense? So if you add three nitrate groups, okay, NO2 groups to that compound, it becomes an explosive known as TNT. If you do the same with phenol, so you change it to add those nitrate groups. So this becomes picric acid. Well, I spent some time on that. Well, TNT is an explosive. Picric acid was used as an explosive as well. It was just very unstable and very hard to work with, and it could easily spontaneously detonate. Does that make sense? The funny part, if you have phenol, you can just mix phenol and nitric acid and boil the living shit out of this for like 2 days, and you're going to get picric acid at the end. So making those explosives in the lab is fairly easy. The problem is the yield is pretty poor if you do it in the lab. So not a single serious person will try to do it at home because it's not justified from the standpoint of price. Okay. You can see that there are a lot of aromatic elements in the drugs, like acetaminophen, okay, which I strongly encourage all the females to take during pregnancy because we need more autistic people to build proper railways in the United States. No, it doesn't cause anything. No. Aspirin and vanillin. This Monday, you did the lab, and one of the compounds that you had to draw was cinnamaldehyde. Basically, it's the compound responsible for the smell of cinnamon. Okay?